Welcome to Pre-Calculus. Today we will investigate transforming exponential and logarithmic parent functions. We'll take a look at two examples, one exponential, one logarithmic. Our first function is f of x equals half times base 2 to the power of x minus 3 minus 4. And I want to start off by getting in view what's the parent function for this graph. So I'm going to create a table. And the parent function is going to be the most simple but most essential part of this transformation. So if I could identify what that is, that's 2 to the power of x. So that's how I'm going to begin with my table, is I want to create a table for that parent function and graph it. So x 2 to the power of x. So we'll use our traditional -2, -1, 0, 1, and 2. And we'll just evaluate these manually. So if I plug in -2 into the power, that's going to give me 1/4. Remember, the negative power bumps that base down into the denominator. So 2 to the power of -1 is half. 2 to the power of 0 is 1. 2 to the first is just 2. And 2 squared is 4. So I'll graph this, and again, this is just to see what does the parent function look like for this transformation. So there's -2, 1/4, -1 is half, 0 is 1, 1 is 2, 2 is 4. And we'll sketch the parent function in. So there we go. That's the base 2 exponential parent function. I'll just sketch in a horizontal asymptote there at the x-axis. So once we have the parent function in view, what I want to do next is describe the changes that f of x makes on this parent function's graph. So one thing that I notice is that I've got 3 numbers in this equation that are different from the parent function equation. So it's definitely this multiplier half, this -3 in the power with the x, and then -4 on the main level. So I want to predict what those will do. And let me start with the translations. The horizontal translations determined by the number either added or subtracted to x. And remember, we go opposite the sign. So if I'm seeing -3, my prediction is that this will move the parent function to the right 3. Now, for the up-down motion, that's the number that's either added or subtracted to the end of the function. And we follow the sign on that one. So if it's saying -4, my prediction is that it will move the graph down 4. So I predicted that it will move the graph right 3, down 4. The last prediction is about this multiplier half. So I see that that's a value in between 0 and 1. So my prediction is that's a vertical compression by a factor of half. And just to kind of think about the other case, if that number had been above 1, we would have said that it would have been a vertical stretch. But since half is between 0 and 1, we'll say it's a compression. The graph will become flatter. So if I were to just sketch in my transformation, I'd say that it had a horizontal asymptote at -4 since it's moved down 4. And then the graph has been moved to the right 3 and compressed. So I expect to see something like that. Now we need to perfect that graph. So the way that I want to do it is by proving it by creating another table and plotting that here along with our parent function. So I'll create this table. It's half times 2 to the power of x minus 3 minus 4. And let's jump over to our graphing calculator to get a set of coordinate points. So we'll head to Desmos. And I'm going to type that function in. So this is the transformation. F of x equals half times base 2 to the power of x minus 3 all minus 4. So I see that that graph has that rough shape that we're looking for, the one that we sketched in our prediction. So I want a table, but I need to respond to the fact that this graph has been shifted to the right 3. So I want to zoom forward. In fact, we'll go all the way to 6. And I don't want to take all those points. In fact, I'm going to start with positive 2. So I'm just going to modify my domain there so that I see 2 through 6. And that catches a nice kind of snapshot of that exponential curve as it's undergoing its growth phase. So I'm going to record this table: 2, negative 3.75, 3, negative 3.5, 4, negative 3, 5, negative 2, and 6, 0. That gives me what I need from the calculator. So I'm going to jump back here and record my table. So we did 2, 3, 4, 5, and 6. And again, the output there is negative 3.75, negative 3.5, negative 3, negative 2, and 0. Let's sketch it. So I'm going to get rid of my prediction. I will leave that horizontal asymptote because that looks accurate at negative 4. So at 2, I'm at negative 3.75. At 3, I'm at negative 3.5. At 4, I'm at negative 3. So you can see that compression. It's not growing as quickly as the parent function. 5 is negative 2, and then 6 is 0. So this is going to look very similar to our sketched prediction, but now this is actually supported by a table. And at that point, I can confirm my 3 predictions. It definitely moved to the right 3, down 4, and compressed vertically by a factor of half. Let's take a look at a logarithmic transformation. So here's f of x equals 4 times log base 5 of negative x plus 3 minus 1. Again, I want to start by saying, what's the parent function of this graph look like? So if I could identify the parent function, it's going to be log base 5 of positive x. That negative is an additional change. So let's graph the parent again first. So x log base 5 of x. And I'm going to go negative 2 through 2 again. But for this function, I really need to use the graphing calculator. It's difficult to calculate directly logarithms. Just to illustrate, if I were to try to evaluate a negative 2, log base 5 of negative 2, and I would say that it equals some y value. Really what I'm saying is 5 to what power would give me negative 2. And in fact, we can kind of make a claim for our first few values. Negative 2, negative 1, negative values, there's no power I could raise a base to that would give a negative output. So in fact, I can make a claim here for these first ones that are negative, that they are undefined. And I can do the same for 0 as well. I can't raise 5 to some power and have it equal 0. So typical of logarithmic functions, they are undefined for the negatives and for 0. We can think about 1 just to illustrate how that would work. It's log base 5 of 1 equals y. So here we'd say 5 to what power would equal 1. And that I can actually evaluate. 5 to the power of the only number that would change any base to 1 is 0. So this is going to be an output of 0. But then I run into some problems. For the next one, log base 5 of 2, there I'm trying to say 5 to what power would equal 2. And that I really don't know. That's an irrational number. So I do need to use the calculator, and I think I need to get a few more points. The undefined ones are informative, but not real useful for sketching the graph. So I'm going to bump this out to 5. And just to help ourselves, let's jump over to Desmos and enlist the graphing calculator to help us with our table. So we'll replace our function with log base 5 of x. You can see there that the graph doesn't cross the y-axis. So definitely our undefined spots for the negatives and 0 are supported by our graph. And then you can see for 2, the output is very irrational as we anticipated. So 2, the output is 0.43. And then let's evaluate also at 3, 4, 5. So at 3, again, you kind of see the irrational nature of logarithmic output, 0.7. We'll say 6.8. 4 is 0.86. And 5 has the output of 1. Because 5 to the first power equals 5. Well, that gives us what we need from our calculator. We got our table, so I'm just going to finish inputting here for 2, just again to catch it again at 0.43. 3 was 0.68, 4 was 0.86, and 5 had the output of 1. So that lets us graph. We'll start with the vertical asymptote at the y-axis. Just sketch that in, and then at 1 we have the value of 0. At 2 we have the value of 0.43, so we got to estimate not quite half. 3 was 0.68, so above half there, 0.86 at 4, and then 1 at 5. So we do have a sharp curve. So the logarithm approaches the x-axis from negative infinity and then veers sharply to the right. And that gives me my parent function for log base 5. So at this point, what I want to do again is make a prediction about how these values, and we should specify what they are, the 4, the negative, the 3, and the negative 1. What do they do to this purple graph of the parent log base 5 of x? So we can start again with the transformations or the translations left, right, up, down. But what we have to do first is some factoring here in negative x plus 3. If I want to catch the correct direction for the left, right translation, I need to factor this. So this is really equivalent to 4 times log base 5 of, let me actually put brackets here to begin. I'm going to factor out negative 1. And what that will give me is positive x minus 3. And then minus 1 on the outside. Now the reason I do that is because it now identifies for me the correct direction for the horizontal translation. It's saying minus once I factor, so my prediction is that this will move the purple graph to the right 3. Let's catch this vertical translation. So that's the minus 1. And again, we follow the sign there. So minus would indicate down, and we'll go a distance of 1. We need to catch then these 2 last multipliers. So let's just decide on this negative 1. Really, that's a negative sign. The number is not it's not going to change the x or the 3, but the sign will change. This is a reflection. Now, it's by the x. So if I've got a negative that's multiplying times the actual domain variable, it's going to be a reflection in the y-axis. And then the last prediction is this 4. And that's like what we saw with our half. And so with the half multiplier in the first example, that compressed the graph. The 4 is above 1. So what that says to me is that this will also be a vertical change, but it's a vertical stretch. The graph should get stretched out vertically by a factor of 4. So those are my predictions. So if I were to sketch this one, the vertical asymptote should move to the right 3. We're going to flip around that asymptote. So the graph will be on the left side because of my reflection in the y-axis. It'll be all moved down one and then stretched by a factor of 4. So if I could predict what this looks like, something like so. But again, we want to prove it. So let's create our table. We'll put x and then the transformed equation 4 times log base 5 of negative x plus 3 minus 1. And I think that we should be good to go with a domain of negative 2 through positive. Let's go all the way through positive 3 just to see if that's in fact the vertical asymptote. My prediction is that 3 should be undefined. Well, let's see. So again, and we're saying undefined there because we think it has a vertical asymptote there. But let's find out for sure. So I'm going to again come over to Desmos, now typing in the transformed function 4 times log base 5 of negative x plus 3 minus 1. So the graph looks pretty accurate to our prediction. Let's see if our table supports that. So negative 2 through 2, we start at negative 2, 3, and then the values go down. So negative 1 is 2.4, 0 is 1.7, 1 is 0.7, 2 is negative 1. Let's see if 3 is undefined. And that supports our hypothesis that there's a vertical asymptote at positive 3. So I'm going to record that table. And let's transfer it here on our note screen. So again, negative 2 is 3. Negative 1 is 2.4, 0 is 1.7, 1 is 0.7, and 2 is negative 1. So I want to, excuse me, sketch that graph. So negative 2, 3. Negative 1 is 2.4. You can see the stretch here. It's even more pronounced than I sketched in my initial drawing. So at 0, we're at 1.7. 1, we're at 0.7, and then 2, we're at negative 1. So here's our function. Definitely, we see the reflection across the y-axis. Everything's here on the left of the vertical asymptote. And we definitely have a stretch there by that factor of 4. And that completes our second example. So thank you for joining for this investigation of transforming exponential and logarithmic parent functions. See you soon.